An ASCO system, upon losing a phase, might exhibit expected behavior. However, the resulting issues, such as power transformer or PT burnout, can be perplexing. The core of the problem often lies not in a voltage surge, as might be initially suspected, but in the characteristics of the power system configuration and the nature of harmonic currents. Specifically, the scenario involves a delta-connected power transformer setup coupled with the presence of third harmonic currents. In a three-phase electrical system, harmonic currents are multiples of the fundamental frequency, which is typically 60 Hz. The third harmonic, therefore, has a frequency of 180 Hz. These harmonics are generated by nonlinear loads, which are common in modern electrical systems. Examples of such loads include variable frequency drives, electronic ballasts, and uninterruptible power supplies. These devices draw current in a non-sinusoidal manner, injecting harmonic currents back into the power system. In a Y-connected transformer, the third harmonic currents tend to circulate within the neutral connection if one exists, or are mitigated to some degree. However, in a delta-connected transformer, the third harmonic currents have a different behavior. The delta connection provides a closed-loop path for these currents to circulate within the transformer windings. Because the third harmonic currents are in phase with each other in each of the three phases, they do not cancel out, instead they add together. This additive effect results in a significant circulating current within the delta winding. This circulating current can cause several problems. Firstly, it can lead to increased heating within the transformer windings. The additional current flow increases the I2R losses, where I is the current and R is the resistance of the winding. This heat can degrade the insulation of the transformer, shortening its lifespan and potentially leading to failure. Secondly, the circulating current can cause voltage distortion. The harmonic currents create voltage drops across the transformer impedance, which distort the sinusoidal waveform of the voltage. This distortion can affect the performance of other equipment connected to the power system. Thirdly, in the specific case of the power transformer burnout, the circulating third harmonic current can exceed the transformer's design capacity. If the current is high enough, it can cause the transformer windings to overheat and fail, resulting in a burnout. A current of 5.6 amps might seem relatively small in the context of a large power system, but within the closed loop of a delta-connected transformer winding, it can be substantial enough to cause damage, particularly if the transformer is not designed to handle significant harmonic currents. The decision to switch to a three-phase ASCO system represents a proactive approach to mitigating these issues. A three-phase system is inherently more balanced and less susceptible to the problems caused by harmonic currents. In a balanced three-phase system, the harmonic currents tend to cancel each other out to a greater extent, reducing the circulating currents within the delta winding of the transformer. Furthermore, a three-phase ASCO system is likely to be designed with consideration for harmonic currents, including features such as harmonic filters or reactors to reduce their impact. These filters and reactors help to block or divert harmonic currents, preventing them from circulating within the transformer windings. In addition to switching to a three-phase ASCO system, there are other measures that can be taken to mitigate the effects of harmonic currents. Firstly, harmonic filters can be installed at the source of the nonlinear loads. These filters are designed to block or divert harmonic currents before they can propagate throughout the power system. Secondly, reactors can be used to increase the impedance of the power system at harmonic frequencies. This impedance limits the flow of harmonic currents, reducing their impact on the system. Thirdly, power transformers can be designed to be more tolerant of harmonic currents. This can be achieved by using larger conductors in the windings, improving the insulation, and incorporating harmonic filters or reactors within the transformer itself. Fourthly, regular monitoring and analysis of the power system can help to identify and address harmonic current problems before they lead to equipment failure. This monitoring can include measuring the harmonic content of the current and voltage waveforms and using specialized software to analyze the data. In summary, the power transformer burnout in the ASCO system was likely caused by the circulation of third harmonic currents within the delta-connected transformer winding. This circulating current led to overheating and eventual failure of the transformer. Switching to a three-phase ASCO system is a good solution, as it provides a more balanced and less susceptible system to harmonic current problems. Additional measures, such as harmonic filters, reactors, and transformer design improvements, can also be taken to mitigate the effects of harmonic currents. It is important to recognize that the presence of harmonic currents is a common issue in modern electrical systems, and that careful consideration must be given to their impact on equipment and system performance. By understanding the causes and effects of harmonic currents, engineers and technicians can take proactive steps to mitigate their impact and prevent equipment failure. In the context of electrical engineering, the interplay between system configuration, load characteristics, and harmonic distortion is crucial for maintaining reliable and efficient power distribution. The presence of harmonic currents can lead to a cascade of problems affecting not only transformers but also other sensitive equipment connected to the grid. For instance, harmonic currents can cause interference with communication systems, leading to data errors and disruptions in service. It can also affect the operation of protective relays, potentially causing false tripping or failure to trip during fault conditions. Furthermore, harmonic currents can increase the losses in transmission and distribution lines, reducing the overall efficiency of the power system. Therefore, a comprehensive approach to harmonic mitigation is essential for ensuring the stability and reliability of the electrical grid. This approach should include not only the measures mentioned earlier, such as harmonic filters and reactors, but also careful consideration of load management and system design. Load management involves optimizing the connection and operation of nonlinear loads to minimize the generation of harmonic currents. This can be achieved by staggering the operation of these loads, using phase-shifting transformers to cancel out harmonic currents, or employing active harmonic filters that inject compensating currents into the system. System design involves selecting equipment and configuring the power system to minimize the impact of harmonic currents. This can include using transformers with lower impedance, employing shielded cables to reduce electromagnetic interference, and implementing grounding systems that effectively dissipate harmonic currents. In addition to these technical measures, it is also important to establish clear standards and guidelines for harmonic distortion. These standards should specify the maximum allowable levels of harmonic current and voltage at various points in the power system. Compliance with these standards should be regularly monitored and enforced to ensure that harmonic distortion is kept within acceptable limits. Furthermore, it is crucial to educate engineers, technicians, and other stakeholders about the causes and effects of harmonic distortion. This education should cover the principles of harmonic generation, propagation, and mitigation, as well as the practical aspects of harmonic measurement and analysis. By raising awareness and promoting best practices, it is possible to minimize the impact of harmonic distortion on the electrical grid and ensure a reliable and efficient power supply for all users. In the specific case of the ASCO system, the transition to a three-phase configuration represents a significant improvement in terms of harmonic mitigation. However, it is still important to conduct a thorough analysis of the system to ensure that the new configuration is optimized for harmonic performance. This analysis should include measuring the harmonic content of the current and voltage waveforms at various points in the system, as well as modeling the system to predict the impact of different load scenarios. Based on the results of this analysis, additional measures may be necessary to further reduce harmonic distortion and ensure the long-term reliability of the system. These measures could include installing harmonic filters, upgrading transformers, or implementing load management strategies. Ultimately, the goal is to create a robust and resilient power system that can withstand the challenges posed by harmonic currents and other forms of electrical disturbance. This requires a holistic approach that considers all aspects of the system, from generation to consumption, and that involves the collaboration of engineers, technicians, and other stakeholders. By working together, it is possible to ensure reliable and efficient power supply for all users and to minimize the risk of equipment failure and service disruptions. The information provided suggests a specific instance of power transformer failure potentially caused by harmonic currents, particularly the third harmonic, in a delta-connected power transformer within an ASCO system. It is vital to expand upon this to give a broader educational context for those who might encounter such issues in diverse settings. Power quality, in general, is an overarching concept that encompasses various aspects of the electrical supply, including voltage stability, frequency regulation, and harmonic distortion. Harmonic distortion, as discussed, is a significant component of power quality issues. To understand the implications fully, consider the following points. Firstly, harmonic distortion can affect a wide range of electrical equipment, not just transformers. Motors, capacitors, and electronic devices can all be susceptible to damage or malfunction due to excessive harmonic currents or voltages. For example, harmonic currents can cause motors to overheat, leading to reduced efficiency and premature failure. Capacitors can experience increased stress, resulting in reduced lifespan and potential catastrophic failure. Electronic devices can exhibit erratic behavior or malfunction due to voltage distortion. Secondly, harmonic distortion can propagate through the power system, affecting equipment and facilities far from the source of the harmonics. This is particularly true in interconnected power systems where harmonic currents can travel long distances along transmission lines. Therefore, it is essential to consider the overall system impact when addressing harmonic distortion problems. Thirdly, the sources of harmonic distortion are becoming increasingly prevalent in modern electrical systems. As mentioned earlier, nonlinear loads such as variable frequency drives, electronic ballasts, and uninterruptible power supplies are major contributors to harmonic generation. The increasing use of these devices in industrial, commercial, and residential settings is exacerbating the problem of harmonic distortion. Fourthly, harmonic analysis is a critical tool for identifying and mitigating harmonic distortion problems. Harmonic analysis involves measuring the harmonic content of the current and voltage waveforms and using specialized software to analyze the data. This analysis can help to pinpoint the sources of harmonics, determine the severity of the distortion, and evaluate the effectiveness of mitigation measures. Fifthly, there are several different types of harmonic mitigation techniques available, each with its own advantages and disadvantages. These techniques include passive harmonic filters, active harmonic filters, reactors, and tune circuits. The choice of mitigation technique depends on the specific characteristics of the power system and the nature of the harmonic distortion problem. Sixthly, standards and guidelines for harmonic distortion are essential for ensuring power quality and equipment compatibility. These standards specify the maximum allowable levels of harmonic current and voltage at various points in the power system. Compliance with these standards is typically enforced by regulatory agencies or utilities. Seventhly, the design and operation of power systems should take into account the potential for harmonic distortion. This includes selecting equipment that is less susceptible to harmonic currents and voltages, implementing load management strategies to minimize harmonic generation, and employing harmonic mitigation techniques when necessary. Eighthly, education and training are crucial for raising awareness about harmonic distortion and promoting best practices for power quality management. Engineers, technicians, and other stakeholders should be trained in the principles of harmonic generation, propagation, and mitigation, as well as the practical aspects of harmonic measurement and analysis. Ninthly, regular monitoring and maintenance of electrical equipment can help to prevent harmonic distortion problems. This includes inspecting equipment for signs of overheating or malfunction, testing capacitors for degradation, and verifying the performance of harmonic filters. Tenthly, a collaborative approach is essential for addressing harmonic distortion problems effectively. This involves the cooperation of utilities, equipment manufacturers, and end users to identify and mitigate harmonic sources, implement best practices for power quality management, and ensure compliance with standards and guidelines. Understanding the potential reasons for failure in electrical systems and power systems, especially those of harmonic distortion, helps to ensure power quality and equipment compatibility for the safety of workers and the health of the electrical grid. The transition to a three-phase ASCO system should be well considered for these reasons. Remember the basic steps to follow, including measuring the harmonic content and design, implementing mitigation, and creating a plan to make sure it all works smoothly.